All right, so today we're going to talk about exponential functions. So you've had quite a bit of experience with exponential functions. So the main goal of my notes today are just to kind of define what an exponential function is, show you the different scenarios, graph a few exponential functions just to refresh your memory, and then that should pretty much wrap up this section. So let's define what an exponential function is. So an exponential function could be broken up into three formats. Okay, so what we know is, or what we've learned is, anytime we talk about an exponential function, this is pretty much a function of the form f of x equals to a to the power of x. Okay, and what we know is where a is a positive constant. Okay, so a can't be negative for obvious reasons, because if a is negative, then you'll just be jumping up and down, and then you don't have a function anymore. So exponential has its own specific shape that we want out of it. So now the question is, well, what happens to my exponential function when a varies, or the value of a changes? So here's what we know. There's actually three things to consider. The third case is actually not that interesting, but the first case is if a is between 0 and 1, how does my graph look? So then we could say f of x equals to a to the power of x has a graph of the following. If you remember, if a is between 0 and 1, as x becomes larger, the y values become smaller. So it kind of has that downward look to it. So what we know is at x equals 0, my y will be 1. At x equals 1, the y value will be a, which a is a number between 0 and 1. So it'll be something like that. So the further you go down, the further you move along, this gets closer and closer to 0. And if you remember, we have a horizontal asymptote at 0. And this just increases really quickly that way. Okay? Now, what if a is greater than 0? So if a is greater than 0, then it's kind of like the shape of this flips. So we could say then f of x equals to a to the power of x has a graph of something along the lines of this. When x is 0, y is still 1. But now, as x moves to the right, this increases exponentially, and then as we go to the negatives, it gets closer to 0, and we have a horizontal asymptote at y equals 0 as well. Okay, and then the last case is if a equals to 1, and this is where we get the not so interesting case. Then f of x equals a to the power of x has a graph of, it's literally just a horizontal line through y equals 1. Okay, so those are the cases that we're going to experience when we talk about exponential functions. Okay, so before we go on and do some examples, let's talk about the laws of exponents. And these laws of exponents you've probably seen since Algebra 1, so nothing new going on here. So we could say if a and b are positive numbers and x and y are any real numbers, then here are the four basic laws of exponents that you've seen. A to the x times a to the y. If you remember, if you're multiplying the same bases together, you're adding the exponents. And then, of course, we have the second property is a to the x minus y is the same thing as a to the x divided by a to the y. And then we have the third condition, which is a to the power of x to the power of y is just power of power. If you remember, we multiply them, so that's a to the xy. And finally, we have ab to the power of x. That just is a to the x times b to the x. So I don't want to spend much time on this. You've seen it before, so I'm just giving it to you so you're aware that you may potentially need to use these. Okay, so moving on. Let's look at some examples. So for example 1, we could say sketch the graph of y equals to 4 to the power of x minus 3. So once again, we're going to graph this using transformations. So what I'm going to do is I'm going to start off with the basic graph, or its parent function, which is 4 to the x. And if you remember, when you graph these exponential functions, there are three x values that we're really interested in: 1, 0, and negative 1. So when x is 1, y is 4. When x is 0, y is 1. When x is negative 1, y is 1/4. And based off of these 3 points, we can pretty much force out the shape of this graph. So we have when x is 0, y is 1. When x is 1, y is 4. When x is negative 1, y is 1/4. And so we get the exponential that looks like this, and we have a horizontal asymptote here. Okay, so now the minus 3 is just a vertical shift. So we're moving it down 3 units. So what's going to happen is, to get y equals 4 to the power of x minus 3 out of this, we're moving every point down 3 units, which means my horizontal asymptote goes from y equals 0 to y equals negative 3. Okay? And then we have over here when x is 0, y was 1, which will now make it when x is 0, y is negative 2. And then here when x is 1, y was 4. Over here when x is 1, y will be 1. And then of course, if this is 1/4, and if I subtract 3 from it, it'll put me somewhere around here. So then there's my graph. Okay, so there's my exponential graph. All right, let's move on to the number e. Okay, now here's a number that's actually a very, very interesting number. You may have talked about how the number was discovered, but I know for a fact that in analysis, you were told that we learned in analysis that e is about 2.71828, and it's just like pi, it's an irrational number, and so it goes on forever without repetition. Now, what I want to point out to you is how this number was discovered, because that's pretty much the more interesting part here. So, how did this number come about? And in fact, e, by definition, is the limit as x goes to infinity of 1 plus 1 over x to the power of x. Which, if you look at this, you might say, well, that's weird, because based on your skills from analysis, you say, look, as x goes to infinity, doesn't 1 over x go to 0? So shouldn't this be 1 to the power of infinity? And the answer is no. Because look, as x is going to 0, this x is going to infinity, which means there's kind of like a balancing act going, which is weird, or is not necessarily weird, but it's really cool also that something like this starts going to that number. So what's the best way to do this? Well, why don't we use our calculators and kind of see how we get this? Now remember, when we're using our calculator, this is kind of going to go into, it's going to start approximating. It doesn't have enough decimal places to fit all of this in there, but you'll see, it'll kind of round this up, but you'll see how this number comes about. So if I go back to y equals, where I was graphing these functions, and if I put 1 plus 1 over x to the power of x, let's put parentheses around this, 1 plus 1 over x to the power of x. Now what I want to do is, I want to make a table for this, and I want to get the table, get the x values of the table larger and larger and larger, and see what the y values approach. Now, if you look at this calculator, above the graph says table. So what's nice is my calculator could also produce a table. So if I press second graph, notice how a table comes up. Now, if I put, let's say, 2, when x is 2, y is 2.25. If I put 5, x is 2.4883. What if I put 7? Then 2.5465. What if I put 10? What if I put 100? What if I put 1,000? What if I put, I don't know, 1 with a bunch of zeros? And so actually that starts giving us an error here. So things are going wrong. But if I do this, so what is it that we notice? As x becomes larger, notice how this is becoming 2.7183, which if you compare it to the number e, 2.71828, and so on. So what this calculator is doing, since it ran out of decimal places, it's just rounding it up. And look, if you round this up, you'd get 2.71828. That rounds up to a 3. So this is basically the definition of what E is. Okay? So let's look at our second example, which we would say graph y equals to 1/2 e to the negative x minus 1. Okay, so we're going to use transformations on this. And it looks like there are actually 3 transformations. We'll start off with the graph of e to the x. This minus means we're going to reflect it with respect to the y-axis. And then the 1/2 is a vertical compression, and the minus 1 is a vertical shift. So let's start off with the graph of e to the x. So the graph of e to the x, when x is 0, y will be 1. When x is 1, y will be e, so that's about 2.7. So here we'll just call that e. And when x is negative 1, it'll be 1 over 2.7. So it's about 1/3 or a little higher than that. So that's what this graph looks like. Okay, so then the next step I'm going to do, like we talked about in class, is I'm going to reflect first. So then let's graph y equals e to the negative x. And if I reflect this, this is a reflection about the y-axis. So I'm basically grabbing all the points and I'm taking their opposite x values. So now, since this was 1 comma e, it's now going to be negative 1 comma e. And then since this is on the y-axis, it's going to stay on the y-axis. And then finally, negative 1, 1 over e now is going to come over to this side, which would be right there. So here's the graph of my exponential. So now I'm ready to take care of the vertical compression. So y equals e to the 1/2 e to the negative x. What is this saying? Just grab all your y values, cut them in half. Your x values are unchanged. So what do I know? At x equals negative 1, this was e. So if I cut that in half, that would put me at somewhere at about 1.35 or somewhere around close to that. So it'll be somewhere here. And then when x was 0, y was 1, so it'll kind of put me halfway. And then if I cut this in half, it'll get even closer to the x-axis. So then it looks something like this. So if you compare this to the top graph, it looks like you've kind of compressed it, and that's why it's kind of going down further. Okay, and then the last graph we'll do is we just move everything down 1 unit. So it'll be y equals to 1/2 e to the negative x minus 1. I'm just going to put this on the same graph here. I'll just use a different color. So just move everything down 1 unit. So my horizontal asymptote will now be at negative 1. If I move this down 1 unit, it'll be here. If I move this down a unit, it'll be here. And then if I move this down a unit, it'll be there. So it looks something along the lines of that. So the purple graph is my final graph. So that basically takes care of exponential functions dealing with the number e. Now, the number e also has more involved behind it, because if you think about the growth and decay problems, I'm not going to do an example, but if you remember from analysis, growth and decay also use the number e. So I'm going to go ahead and give you the formula. For homework, you'll use this. If you remember, the growth and decay formula had something like this. The number of bacteria or some population in a culture was defined as n sub 0, which that was your initial population, times e to the kt, which k was kind of like our growth or decay coefficient, or the rate, the growth rate. So if k is greater than 0, we have growth, and if k is less than 0, we have decay. I know that our analysis book gave two different formulas, and I always found that redundant because this is the same formula. So if k is positive, then this will be a growth formula. If this k is negative, then it'll be a decay formula. So this is what you want to do, or what you want to use to solve exponential growth or decay problems. Okay, so just keep that in mind. And what's even more important, and what's a nice result that we're going to get, is later on in this class, we're actually going to derive this formula. So I think in analysis, even before then, Algebra 2, when you dealt with this formula, it was kind of given to you. And they told you, or your teachers in the past told you, just memorize it, accept it from the way it is. And it's completely understandable because you need calculus to derive this. And that's why I love calculus so much, because we use it constantly to kind of show why things work the way they do. So I promise you, sometime throughout the year, we're actually going to derive this, and you're going to see how this formula comes about, which actually makes math so much more relevant and so much more interesting. Instead of just memorizing, we're understanding why things work the way they do. So that basically wraps up section 5. And feel free to, once again, as always, if you have questions, don't hesitate to ask questions. I'll be more than happy to clarify anything that was not clear here.